talking about gravity. Now, you can consider these notes if you wish, but this is just sort of some more background information. You can sort of thinking about gravity a little bit. If you want to write it down, fine, but I'm not likely going to wait for you.
Will you be uploading these?
Oh, absolutely.
Oh,
Yeah. Okay, so let me get my prop that I'm going to need here. Gravity, right? So this dude named Newton. Now this was happening around 1665 during the bubonic plague, the Black Death that ravaged through Europe because of rats and poor hygiene kind of thing. So they were actually closing down, much like when we have snow days, they were closing down universities, and so they sent Newton home. And so he had nothing better to do, so he sort of was feeling a little depressed and started thinking about things that dragged him down. How about that version of it? Is that one better, Jared? That was a little better? Okay, so anyways, he was home from university thinking about gravity. About a century before him, a gentleman by the name of Johann Kepler developed laws to explain the motion of the planets. Now, way back at the start of the year, I talked about how the planets were called wanderers because they wandered through the sky, and they kind of did this loop-de-loop kind of thing. And so another scientist by the name of Tycho Brahe, who actually had a gold nose because he lost his nose in a duel, that's a true story. His name was Tycho Brahe. He got into a sword fight with another guy, and the other guy cut his nose off, so he had a gold nose.
Wait, wasn't he like a sideshow guy?
oh yeah.
I think so. Some guy.
I don't know. He was like an exceptional. He built I don't know if he built a telescope because that was Galileo, but he built an observatory. And he was an exceptional. He was very good at detail. So years and years and years of data. A guy by the name of Kepler came up with some crazy mathematical formulas that described them, but they didn't really know why they moved. So Newton himself was wondering if the same force that caused an apple to fall to the ground from a tree was the same force that was causing these planets to wander through the sky. And of course it was. It's what? Gravity. Exactly.
Crazy.
So this led Newton to what we now know as the law of universal gravitation. And you saw this in last week's TED Talk. And it says, and no, you don't have to write it down, between every two objects there exists a force of attraction. I gave this to you like a while back, right? Never me being attracted to the pencil sharpener, right? This force is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Now that's crazy talk, right? So what does that mean? It means proportional to the product of their masses. So if you're a big person, you have a greater gravitational field. My desk is large, it's much larger than me. I am attracted more to my desk than I am to, say, the scale. Thank you. The scale. Okay? Because it's much more massive, right? It's also inversely proportional to the square of the distance between the centers. So, in other words, as I get farther away from the desk, I'm less and less attracted to it. Okay? As I get closer, I'm much more attracted to it. And that's an inverse square law. So in other words, if I'm twice as far, it's actually 4 times the strength. And more on the inverse square law in a bit. I'm kind of giving you just some rough background. Now the formula, the mathematical law for this is F equals big G m1 m2 all over r squared, where m1 is mass 1 and m2 is mass 2. And G, give Josh a little nudge there, wake him up. Big G is what's known as the universal gravitational constant, or 6.67 times 10 to the minus 31, I believe, divided by r squared. Yeah, it's pretty tiny. And what I mean by this is, okay, there's an equation form. When I show you the picture, it makes a little bit more sense. So I've got mass 1 here, mass 2 here, and r is the radius, or the distance between them. Distance between their centers. Okay? Now this is true throughout the universe. It's a universal law. And scientists will use it. Certainly astronomers will use it. The folks at NASA will use it when they're sending space probes out deep past Pluto. They use this to slingshot things around big planets. They used it in The Martian, I think, right? Didn't they do like a slingshot? Oh yeah, that's right. They came back to Earth, and instead of landing, they slingshot around, and so that they could save time and go back, right? That's exactly what they did.
Can we watch that movie at the end?
Now, before you get all freaked out, there will be no problems that use that equation. So don't worry about it. What's going on there, Danielle? Oh, screen.
They even painted the door.
Yeah. There will be no problems that will use this formula, so don't worry about that. Okay, now, this is something that you should know. The region around a mass in which a second mass will experience a gravitational force is described as a gravitational field. A gravitational field. My desk here at the front, my big wooden desk, has a gravitational field. Everyone in the room has their own gravitational field, right? Some of you have a stronger field than others, depends on your size. So the region around this mass, around the desk, in which the second mass will experience a gravitational force is described as a gravitational field. If I throw the foam ball towards sort of the side here, theoretically it's being attracted towards the desk, right? But it's also being attracted to Adam and Travis and everyone else sitting back there, right?
Yeah.
So it's down.
But if they were in space, it's just the ball on the desk.
Then it would be attracted. But he's orbiting. Unlikely. We're talking, like, remember I said 6.67 times 10 to the minus 31. So like 30 zeros. But this idea of a gravitational field is something that we're going to keep coming back to. Okay? And the strength of the field at any place is defined as the gravitational force that a unit mass would experience at place there. I'll let you write that down if you are writing stuff down, and then I'll explain. Okay, so what I'm talking about here is the strength of the field at any place is defined as the gravitational force that a unit mass would experience at place there. So I just so happen to have a 1 kilogram mass right here. Right? And in the Earth's gravitational field of 9.8 newtons per kilogram, it experiences 9.8 newtons. 9.8 newtons is that's a hefty amount. And you can easily verify that by putting it on a scale like this, and you'll see that it weighs about 9.8, right? So the Earth's gravitational field is described as how much force does a 1 kilogram mass experience. If we were to take this to the moon, it would be like there, 1.6. I don't know Jupiter. It would be more than 9.8. I don't know. This strength is represented by the letter G, right? So 1G is represented, or 1G is 9.8, right? And you sometimes hear about astronauts or even race car drivers experiencing 3 Gs. So they're experiencing an acceleration that's 3 times 9.8. Yeah. Now, when you draw a gravitational field, the field lines, and more on this in a bit, are closer together where it is strong, and where it is weaker, they are further apart. And you really should draw this picture because you are expected to know this. So there's Earth in all its glory, and you can just barely see the arrows there, so I'm going to fill them in a little darker for you. These are the gravitational field lines. They look a lot like vectors. They're not. It says where the field lines are close together, it's strong, and where it's weaker, it's further apart. So I'd like you to add this in as well. So right in here where they're close together, this is a strong gravitational field. And way out here where they're farther apart, it is weaker. Okay? So we would even say it's the density of the lines. When they're dense, when they're close together, it's strong. So those are not vectors. They are field lines. Okay, so what this implies is that as you climb an altitude, the gravity actually gets weaker. Okay? So if I were to draw a graph, altitude, gravity, what would be the shape of it? It was up there before and I erased it, maybe you saw it. Go ahead, Adam.
Would you like a slide
Would
line?
it be curvy?
Yeah.
Would it be curvy like that? Or would it be green and would it be straight like this?
Like that at the end.
The green one or the blue one?
Oh,
You're not sure?
I just saw that before.
Yeah. As the altitude gets higher, right, as you get a bigger altitude, the gravity has to go down. But is it like this, or is it curved like that? Well, the answer is,
Yeah.
okay, because it's an inverse relationship. You might remember that from like the second or third day. Inverse relationship. In fact, it's an inverse squared relationship, which gives it kind of a steeper kind of curve to it, in fact. Okay? On this graph right here, this is 0. So at 0, the graph is going to be about 9.8. But you will notice here at about 400 kilometers up, the gravity is 9.5. Well, let's draw that and then think about it for a second. Okay, so I want you to realize, you don't need to write all the notes down on the side, but I want you to realize that at about 400 kilometers straight up, like we're talking the distance to Winnipeg, straight up, gravity is still 9.5 newtons per kilogram. That's about 95%, 96% of what it is right here on Earth. But aren't the, and now this has been around for a while, we don't have space shuttles anymore, do we? Because they decommissioned them about 10 years ago. They don't use them anymore. When the Americans go up to space, they have to go to Russia to launch. Because that's where the Russians are the only people that are sending humans to space station. They're the only people that have the technology. The United States does not have the technology to send someone to the space station themselves. Only the Russians. Well, since the one of the shuttles, there was 2 shuttle accidents. One when I was about your age, about 1986, 85. Yeah. They had a shuttle that exploded on launch about 30 seconds after launch. It kind of went. And actually, that was the first shuttle where it was a civilian on board. It was a teacher, actually. A school teacher went on board, and that was the Challenger. And then the Discovery space shuttle, when it was returning about 10, 12 years ago, on re-entry, it missed the angle of re-entry, and it burned up in the atmosphere. Coming back. Yeah. Pardon me? It blew up. There wasn't so much giving up on it. Oh yeah, they gave up on the program. Yes, they. Only the Russians send people to space. But they launch for all countries. Like Americans go and they'll put 1 astronaut. It's only a 3-man crew though in the Soyuz. Anyways, you guys have seen the video. You know Chris Hadfield, right? The Canadian astronaut. I'm reading his autobiography at home right now. It's good. Yeah. Actually, there's a good part in there kind of was making me think of physics because he talks about grit and perseverance and stuff like that. So bring that in for it. But anyways, you've seen those videos where they're floating around up there. So how can they be floating around at 400 kilometers up if the gravity is 9.5? Adam?
How does the space station going like that?
Because it's
going so fast around the Earth.
okay. Why does that make it them look weightless?
Because when you're falling at fast speed here on Earth, you're also seeing weightless.
Like when I throw the ball at T, does gravity affect it?
Yes.
In fact, it's doing what? It's calling it, bringing it down, right? And if I throw it really fast, does it fall down at all?
Not as much.
Not as much, but that's because it takes less time. The force is still the same. There is no force going sideways. Remember, it's already let my hand drop, right? The motion stays in motion. So what is causing this weightlessness feature? Well, let me show you here. 9.8, right? What if I were to drop it?
It goes 0.
Will it go to 0?
Yeah, we talked.
Did we do this already?
No, we talked about it.
See, it went to 0. Look at that.
Did it go to 0?
Yeah.
Let's try again.
Oh, not 0.
Did it go to zero? Of course it did. Now, if you can imagine that falling, like if I jumped out of a plane with this, what would it show?
Zero.
Zero. How come?
The velocity, it's falling velocity and gravity are equal.
Yeah, they're both falling, so there's no force required, right? There's no tension between them. Exactly. So what does this have to do with the astronauts on the ISS? Well, here's the answer. They are actually, anything in orbit is actually falling forever. Free fall. Thank you. They are falling, and when I throw the ball to T, it falls and it curves down, right? But the ISS is traveling huge speeds, right? Really, really, really fast. The space shuttle is traveling at a great horizontal speed, and if I show you the picture here, come on, right? So not only is it falling, but it's also, gentlemen, moving sideways. And so when you add those two together, which way does it go? Well, it goes there. So it is fallen, but it's gone sort of like around the corner of the Earth. And so when it gets to here, right, it's going this way, also falling, so it ends up going that way. And so it simply continues to go forward and fall forever. But it never lands. Guys, you need to listen. It never lands. Because the Earth is sort of out of the way there now. And if you were to complete it, then it looks like that. Adam, you seem to be more concerned with the Pringles in the bag than gravity. Please listen. Okay? So that's how orbit works. It's continuing to fall over and over and over again. If I were to take my little scale up, get a plane and jump out, what would it read? Zero, right? Zero. So the vector sum of the horizontal motion and gravity causes the shuttle or any orbiting satellite to orbit the Earth at high speed. Since gravity is constantly pulling down the astronauts, they are in constant free fall, which is called apparent weightlessness. Apparent weightlessness. They actually do have a weight. It's the force of gravity. You just can't measure it. There is a weight. There is a mass. There is a gravity. There's a weight force. You just can't measure it because there's nothing that's not falling to measure it by. Does that make sense? But I want to show you a video. Okay, so I quite often get kids saying, hey, well, sure would be nice to have a list of formulas, Mr. Bennett. Thank you. Anybody see any problems with that list of formulas?
Yeah, I know.
Here's the problem with the list of formulas when I give them, is that if I make a mistake,
You make
You make a mistake.
I did.
Oh.
Where is it?
Oh.
First one, V bar is equal to
D over T.
Oh.
D over T, isn't it?
How did you? You got me confused there. I don't think it's it.
Okay, so example number one, the demon drop. Sounds scary. It's a ride at an amusement park. You watch it and time its free fall at 1.5 seconds. So this is the thing I do at like amusement parks. Figure out how fast they're going. It's 1.5 seconds. How fast is it going when it reaches the bottom? So what do we know? Well, we know this is happening on Earth, so our acceleration is minus 9.8. And it doesn't come out and say it, but can we assume the initial velocity is zero? Think so. And we know that our time is 1.5 seconds. And I'm trying to find the final velocity, right? The VF. Okay, so what can I get with A and T? Because there's a formula that has A and T in it. 1.5 seconds, right there, right? Delta V over delta T. So minus 9.8 is equal to my change in velocity divided by my 1.5 seconds. I get basically this all the problems here are basically all the problems that you've done horizontally and now just turned up and down. So you're going to find a lot of the thinking is pretty much the same. It's probably you're going to find it relatively easy. Again, because I keep recycling the same concepts, right? So minus 14.7, that's the change in the velocity, but because, right? Because my initial velocity is 0, well, therefore my final velocity is also minus 14.7 meters per second. I was pleased to see many of you did units good on the test, so that was good. So that's how fast it's going when it reaches the bottom. And now the question is, well, how high is it? Well, the displacement formula has V bar in it, doesn't it, right? V bar equals d over t. But I don't have V bar. Exactly. V bar is VI plus VF all over 2. Yeah, V bar can equal more than one thing. So the initial velocity is 0. My final velocity is minus 14.7 divided by 2, which is, of course, minus 7.35. They found me. I moved. So what's the next step? Yeah, minus 7.35 is equal to d over 1.5. And this ride is only 11 meters tall, which is kind of lame. It's like the height of the gym. Okay, well, let's try this one. Maybe this one's a little higher. We'll see here. So this time, example number 2 here. We're tossing a tennis ball up. Do you hear me talking, you guys? Okay. Tennis ball is thrown upward with an initial velocity of plus 22.5, and it's caught at the same distance above the ground from which it's thrown. So what they're saying there is, I'll draw my stick human. And here's the ball. And it goes up, and it's caught at the same height. Okay? It's up to you, yeah? Your notes, right? Like, what's going to help you understand later? So the initial velocity is 22.5, right? How high does the ball rise? So what is this distance here to the top? Well, we know that the acceleration is minus 9.8. Do we know anything else? Gravity is minus 9.8.
So when we're switching to acceleration, we just make a negative.
Yep. Well, the thing that you know is that the final velocity is actually 0. Where? Right there at the peak, right? So it's 0 at the top, right? So with VI and VF, I can find delta V. So that's going to be 0 minus 22.5 or minus 22.5. But the height, the formula that has height in it, the d, is going to be V bar equals d over t. Do I have the time yet? I do not. I do not have time. Can I find time?
You have to find average velocity first.
I do, but I got to find time too, right? So I can find delta V, we just did. And our acceleration is minus 9.8, and that's all over the time. And so my time is 22.5 over 9.8. That's calculated. This is the one that needs light. Gotta get all my calculator going on.
Oh, right there.
2.3 seconds? Is that what you got? 2.3 seconds is the time up. So how, oh, we still don't even have the average velocity yet, do we? Oh boy. No, we don't. So that's going to be 22.5 plus 0 divided by 2. That's 11.25 meters per second. And now V bar equals D over T.
Very similar to last.
These are all that's happening is now it's a vertical question. No, it's actually positive because it's going up, right? Because this is the initial and the final. This here is the change in the velocity. Right? Remember, those things are different things. So we're going to multiply here, and we're going to get 25.9 meters. The ball goes up. That's not too bad. What about part B, where it says, how long does the ball remain in the air?
Well, we already have
We have, but that 2.3 is only the rise. So the total time, TT, 2.3 plus 2.3, 4.6 seconds. Because the 2.3 is the time up, and then 2.3 back down, right? It's minus 9.8 up, and it's minus 9.8 down, isn't it? Gravity. Doesn't matter, it's the acceleration. So you're still thinking that acceleration and velocity are different. If you throw it up higher, it's just going to go further up. It's going to take longer. It's going to take 3 seconds to go up and 3 seconds down, right? I think you could try number 3 on your own.
Oh,
Yeah. I gave it to the morning class, and they were quite capable of doing it. So you give number 3 a go. Okay, so what do we know? Well, technically the displacement is minus 70.1 because it's falling, it's down. What's the acceleration? Minus 9.8. What's the initial velocity? 0. We want to know how fast you're going. We want to know VF. And we got the time being 3.8 seconds. So I see A and T, so that tells me I can find the change in velocity. A is always minus 9.8, unless otherwise noted. Well, if it was happening on the moon or something, right? They'd have to give it to you. It would have to be on another planet. Sure. So the change in velocity is 37.24, and that's actually negative, right? And we want to know how fast it's going when it reaches the bottom, so we're looking for the VF, right? So VI is 0. Do I even need to write this part out?
No, you can just stop right there.
You can just say it. But you should at least, yeah. That's it. That's all there is to it. Did I even use the 70.1?
No, you could have.
Those are 2 steps that are done now. It's like a country song.
There are 2 different ways, though.
Okay, last one. Now, just because I'm a heck of a nice guy, I'm going to cross out A and B. Suppose that a ball is dropped from a tower that's 70.1 meters high. How far will it have fallen during the fourth second? During the fourth second. So after 1 second, it falls there, right? After 2 seconds, it falls to there. After 3 seconds, it falls to there. And after 4 seconds, it falls to there. The fourth second is, well, this is the first one. That's the second one. That's the third one. The fourth one is between 3 and 4, right? The fourth second is between t is equal to 3 and t is equal to 4. So how far does it fall during that time? Well, you got to figure out where it is at 3, where it is at 4, and then subtract, right? So how far does it fall in 3 seconds? Is that not kind of what we just did right here? Oh no, maybe not. How far does it fall in 3 seconds? Well, what do I know?
3 seconds?
Yeah, it's during the fourth, which is between 3 and 4 seconds. This is where it is after 1 second. This is where it is after 2 seconds, where it is after 3 seconds, where it is after 4 seconds. Did you see me drawing it, Danielle? The initial velocity is 0, but I want to know how far. I want to know the d, so to find the displacement, I need the average, right? And to find the average, I got to find the VF. So I got to find the change in velocity. That's what I got to start with. A equals delta V over delta T. I got to find the change in velocity after 3 seconds. That's what I got to do. Minus 29.4. That's how fast it's going after 3 seconds, right? How fast it's going after 3 seconds. And now I can go initial, final, divide by 2. So the average is 14.7. Negative, because it's going down. And now I can go V bar equals D over T. 3 seconds. So it's fallen 44.1 meters after 3 seconds. Why is there so much writing? Why are there so many words in books?
Why is I think the third second out of the fourth?
It's during the 4th second. It's not after 4 seconds, Danielle.
During would be 4 seconds.
There's so many questions.
Okay.
Finding after 3 seconds right now.
From 0 to 1 is the first. From 1 to 2 is the second. From 2 to 3 is the third full second. And from 3 to 4 is the fourth second. I don't want to know how far it's fallen after 4. I want to know how far it's fallen during the 4th second.
So the fourth second would not be 5 or 4 to 5?
No. 0 to 1 is the first. Well, here's 4 to 5, Kaylee, right? You're just not agreeing with me.
I don't understand why it's not like it's during the 4th second. So the 4th second, they need to start with 4.
No,
All right, so what's the next step? Well, this is how far you've fallen after 3 seconds, so what do? Hang on with me, guys, hang on. What do I have to do to complete this question? Hello, still working over here. This is how far you've fallen after 3 seconds. So now we got to do exactly the same thing except 4 seconds. Okay? I'll come over and I'll show you guys. I'll come over and I'll re-explain to you guys, okay? Plus, it gives me a little bit of time to figure out a new way to explain it to you. It would be. No? Okay, so after 4 seconds, it's fallen a total all the way from the top of 78.4. Right? So how do I find how far it's fallen during the 4th second? Yep, 78.4 minus 44.1. It's asked how far, so we can just go with, yeah. So it falls 34.3 meters just between 3 and 4 seconds, right? Just between 3 and 4 seconds. How come that's almost as far as it falls after 3 seconds total? Because it's going faster and faster. It's like the fat cat falling off the roof, right? The dots are going to get farther apart.